Thank you very much for coming. I'm going to talk about the Bayes linear emulation and history matching, the methodology behind this stuff, and then give you a few examples of it sort of working and doing its sort of thing. So I'm mainly going to focus on the sort of concepts and why we think this is sort of a good idea, because there's some well, we think interesting ideas behind this, and we just want to give you a little taste of this before you then actually get on to using it. So we're going to describe and demonstrate these Bayesian techniques, and it's sort of, we're Bayesian statisticians, so it's rooted in a sort of Bayesian world for analyzing complex models that underlie the HMER package. So we're going to start, now I'm going to use this quite a bit, so I thought I'd just start straight away. So we're going to start by assuming the epidemiologist, that's you, has a model. And if you think about what a mathematical model is, it's sort of like a function. So a model, we're going to denote this as f of x, where f is a vector of outputs of interest, like the incidence, prevalence at various times, all of the things you might want to care about. And the input to that model, x, is a vector of input parameters, which would be things like transmission rates or contact rates or whatever you need to put into the model to make it run. So you choose parameters which go in, you run your model, it gives you stuff out, normally say on a time series over time. And that's basically a function. So I'll come back to that and we'll define it a bit more carefully later on, but that's where we're starting. Anyway, we're going to discuss the principles of analyzing that function and comparing it to data from the real world. But I'm going to try and do most of these principles just using pictures. So there's going to be lots of plots so we get onto the same page. I was told there's quite a sort of spread of ages in the room. So my apologies if I start at a low level and you're already on top of this. But hopefully we'll just gather everyone up and walk them all along together. So we'll discuss the principles of this using pictures, and then we'll apply it to two classes of model. One is Mukwano, which is an HIV model. Another one is a TB model that we did recently, which was done using HMER. So I'll show you that sort of working, what it does. And we'll describe the core scientific questions a modeler may wish to answer and how HMER can help. Now, first major question. Is the model currently consistent with the observed measurements, the observed data? That's a kind of fundamental question. You build a model, is it consistent with the observed data? Well, to answer this really, if your model is slightly large, complex, if it's got quite a few parameters, if it takes a little bit of time to run, well, we need emulation. Emulation helps us combat the speed and dimension problem. I'll talk about that quite a bit. I just want to tell you what's sort of coming. We need things called implausibility measures. That's our way of comparing the model to observed data, and involves all the sort of uncertainties in that, observed errors, things called model discrepancy, et cetera, et cetera. And then we do a process called iterative history matching, which is a global parameter search strategy. That's where we search through all those input parameters of the model, that X vector I just talked about. We search through all that space to try and find where the model will match the data and where it won't. So that's the first sort of question. Does the model even fit? But the second question is almost more important. And the second one sort of answers the first, incidentally. What is the set of all input parameters that produce model outputs consistent with known measurement? So where can I run the model? What parameters can I choose, which will run the model and then give output consistent with observed data? And that word consistent is, of course, fun all by itself. Now, we will identify and analyze this set. That's the kind of goal of history matching in a sense. And now, once you have that, you can do lots of wonderful things. You can use this to make future predictions. You can analyze the effects of interventions, for example. You could design future data collection campaigns, for example. So there's all sorts of stuff that you need to do. Today's workshop is about identifying the sets. These other things are cool sort of spin-offs from this stuff. But let's look at that second question in more detail, because it hides some subtlety. So I've just repeated it there, and we're going to identify the set. So the question here is why? So why not just optimize, for example, to find a decent run of the model that is a good fit to the data? So we could just plug our model into some optimizer, it'd explore parameter space, try and find a single run that's pretty good, and you could just do that and publish that. Well, why do we need to find the set of all input parameters consistent with the data? This is our kind of goal of history matching, and it's key, and it underlies everything we're going to do today. So I just want to spend a few minutes talking about that principle because it's really quite important. Richard alluded to it incidentally in his introduction about the issues of this stuff. So I'm just going to show this via pictures. This is just a sort of fake picture just so we can talk about the principle. There's nothing kind of real here, but it's just so we can talk about the principle. But imagine you had a model which had two parameters. It has input parameter X, oh, sorry, this little guy's in the way, but anyway, input parameter X1 on the bottom, input parameter X2 on this axis here. So X1 might be some, say, transmission rate in schools, for example. X2 might be transmission rate, say, in offices, for example. And you can run your model at various points in this parameter space. And what we're seeing with these colors is some sort of goodness of fit to data. You could think of this as a likelihood if you want. You could think of it as a shape of a posterior if you want. You could just think of it as where the model fits the data quite well. So white is sort of good. Green is bad in this case. But really, anything that's beating yellow, anything that's above yellow is essentially a sort of acceptable match to data, as in various statistical arguments might say you should consider those parameters as viable, whether you're a Bayesian statistician or a frequentist or whatever. So really, that's the set of parameters that we want to discover. The green stuff's rubbish. Now, here's the problem, just in a word. If we choose things like optimizers, an optimizer might start out in the wilderness here. And depending if it's a deterministic optimizer or if it's something like a genetic algorithm, which has some stochastic component, it might wobble around a little bit. Or if your model stochastic, that can make things a bit harder for these guys, but it'll jump around a little bit and then it might find the top of the hill. But the problem is optimizers are just built to find the best run. They're not built to find all the parameters. And as we'll see soon, that becomes a real problem. They'll find the top of the hill. And I talk to a lot of people who use optimizers and I say, well, what about the uncertainty on parameter X1 and X2? And of course, they say, well, you know, what we can do is we can just take the last several steps of my optimizer, you know, the last several steps, which give you like, you know, 20 runs that were quite good. And we can use those to try and find our uncertainties on X1 and X2. But what that equates to is using these dots, that set of dots, as a representation for this whole shape here. And that's not really right. I mean, these dots don't represent that whole shape at all. And here's another optimizer running, gives you those dots. Here's another one that gives you those dots. Here's another one gives you those dots. Because the problem here is that optimizers are not built for exploring parameter space to find all possible good runs. They're just built to climb hills. So what would we really want to do? And incidentally, optimizers are good for many, many tasks. I'm not knocking optimizers. I'm just saying they are not right for this particular task. What would we really want to do? Well, if we had tons of computing resources, we'd just blitz the space. We'd just evaluate the model all over the input space. So every one of these dots corresponds to you picking a value for X1 and a value for X2 and running your model and it producing some outputs. And you're either sad if it's in the green area or you're happy if it's over here. So we just cut down and say, well, all these runs are pretty good. All these runs are really quite nice fits to the data. And really, it's this whole set we want to use. Now, why is that true? Why does it really matter? Why don't I just go to the top of the damn hill? Well, really, all of these points could be viable, realistic versions of the reality we're trying to mimic. What they mean is that the underlying rate parameters could be down here, could be up here. So the problem is, of course, if you don't capture this whole set, you lose something. So if someone were to ask you, could it be the case, say for COVID, for example, that there's a lot of transmission in schools, but not so much in offices? Well, that would correspond to runs down here. Or could it be the case that there's less transmission in schools, but a bit more in offices? Well, that would be the points over here. Now, if your data tells you that all of these are viable, you have to say there is some uncertainty about that, and it could be either or of those cases. And your future predictions and interventions will depend upon you knowing that. So that's the inference question. You're inferring what's going on. And if you haven't got all these points, you miss out. But let's just be a bit more cut right to the chase on this. That the real problem is whenever you use these runs for things like prediction, you really get burnt by this. So I'm going to divide those points into blue and red points. And I'm going to imagine that we've just found the blue ones. So imagine we use some algorithm and it found some blue ones. We evaluated some of these blue dots. And here's the actual output of the model. So here I have time in months, say. Here I have some observed data. And those blue dots, each one of those blue dots, say, I evaluate a handful of them, and they give me these blue lines here. So they go through the data. As I said, these are decent runs. They're going through the data, and that's cool. And I run them into the future, and they give me some sort of prediction into the future. And that looks great. And if I were to use these, again, depending on what sort of flavor of statistician I am or what technique I might want to use, I can use these to get some prediction intervals using various underlying statistical models. But you can see how one would do it. Prediction interval here, prediction interval here. It all looks happy. But of course, it's not happy. Why is it not? Because those were just the blue dots, right? I've missed the red dots. I didn't find them for some reason or another. But what happens if I did find the red dots? The red dots look like this. They match the data as well. But when I run them into the future, they give different predictions. They do different stuff. And they would give me these predictions here. Blue predictions, red predictions. They give me quite different results. So the problem is that I had all these viable fits to the data, but if I only find some of them, this greatly biases and affects my future predictions. So this is the reason why we want to explore the full parameter space. This is the reason why uncertainty on input parameters really does matter. And in fact, uncertainty throughout this problem will really matter. For example, the uncertainty on the widths of these observed data points matters. Anyway, what would we really want to do? We'd want to find them all. We'd want to have predictions which encompass all of this information. Maybe they're uncomfortably wide, but maybe that is the truth given the information we have, and we can't really sort of shirk from it. Okay. So incidentally, when you're doing this sort of stuff, quite often it's worse because the likelihood you might have, or whatever fitting metric, might have different blobs which are kind of disconnected, and optimizers might only find one of them, as you can imagine. And we'd really want to find both of them, but we have that whole blue sort of red problem just between the two modes. So the same problem exists, but it's even worse. It's very likely that we might find the blue mode, but not the red mode, et cetera, et cetera, et cetera. So that's that sort of basic reason. Why do we want to exhaustively explore the parameter space? Is to protect us against problems such as that. So how do we actually do this? Because that's all fine, but how do we kind of proceed? Well, how do we do this, especially when the model is too slow to simply blitz the parameter space? I can't just cover it with points everywhere. And that blitzing idea of just covering it with a billion points, that gets exponentially harder with larger input parameter dimension. And we'll say a bit more about that in a second. So we're now going to attempt to describe the Bayes linear emulation and history matching approach using a simple 1D toy model and a lot of pictures. So hopefully you'll follow the simple 1D case, and then we'll just jump to 22 dimensions for some of the actual disease models. Smoothly, I hope. Fantastic. So here's a simple, very simple 1D model, just so we can see what the hell is going on, so you can sort of get the underlying principles of this. So say we're interested in the incidence of a disease in the early phase of an epidemic, and it's just really early phase. We will model this incidence as some function. It's going to be f of x, and I'm also going to include time explicitly there, just for clarity. It's going to disappear soon, where x is a transmission rate parameter and t is time. So we think that f satisfies the very simple differential equation or model. I'm going to keep it dead simple. It's start of some outbreak, and we're going to say the model has some differential equation. df by dt is equal to x by f, which gives me that f is an exponential. So some differential equation that incidentally represents your disease model. And this is the simplest one we can do. F is equal to f naught times the exponential of xt. Now, that's like that. It's a bit like the start of an epidemic. Obviously, it doesn't even handle herd immunity or whatever, but I just want something really simple so you can see it and so we can talk about it. So we'll temporarily assume the initial conditions are equal to 1, and we'll let the system run from t is equal to 0 to 5, and we'll say we're going to measure the system with error at t is equal to 3.5. So the model features this input parameter x, which we want to learn about. So this is the game. We have some model here. It has some behavior. It has an input x that we want to learn about, and all we're going to do is measure the system at 3.5. Note that normally we would not have the analytical solution for f of xt. We have it here because it's a toy example and we're playing with it, but normally we don't have that, and it takes us time to evaluate that. More on that in a second. Okay, so now we can just do this. One model run. If I run this model, I pick x is equal to be 0.4. That's my transmission rate. I run the model. It looks like that. Again, I'm keeping it dead simple just so we can see it. And that's all fine. If we didn't know this, we'd have to numerically solve it on a computer. That might take some time. But I can run the model in lots of different places. I can choose x to be 0.1, red line. I can choose x to be 0.5, purple line, and a few in between. And that's all fine. However, the key thing is we're going to measure this model at a t is equal to 3.5 seconds, weeks, months, whatever you like. So we're going to measure it here. So someone's taken some measurements of what they think the incidence is. And the measurement is a data point, but it comes with error. It's not an individual point. It's actually comes with some error state. So really, the main question here is, and this is the inverse question or the inference question, if you're familiar with these things. The major question is, which values of x ensure the output f of x at t is equal to 3.5 is consistent with the observation? Now, it would seem that x, just by eye, we can see that x has to be at least between 0.3 and 0.4. I can see that just because the observation is between the green and blue lines, and look up here, x is 0.3, x is 0.4, so it's somewhere in between those two. But what do we really sort of do with this? Well, all the other sort of model statements at different times are a little bit irrelevant to us right now. We just want to learn about x. We've only got one measurement, so let's just talk about this one right here. So we can discard other values of f and think of this f of x at t is equal to 3.5 as a function of x only. It's now just a function of these input parameter x. So we're going to define f of x, and that was the f of x I talked about right at the beginning of the talk, to be that function at this time. And now I can just redraw this graph. I can take this graph and forget the time axis. That's irrelevant to me now. I'm going to now put x on the x-axis, which seems appropriate. So that's our rate parameter, our transmission rate parameter value x. It's now on the x-axis. So that red dot there and that purple dot there maps to that red dot, that purple dot there. Now, so we can plot the instance f of x as a function of the input parameter x. So now our observed data point, which was this guy here, now on this graph becomes a horizontal line because we're interested in hitting it for any possible value of x that's good. The observed error, this error bar here, maps to this picture here, maps to these dotted lines, plus or minus, saying we've measured this, but we're not quite sure about it. So now this is our picture, and this is in fact is the model calibration picture. This is the inference picture. And my apologies for any people who work on calibration all the time, because this will be quite straightforward, but I just thought we'd get to this picture together so we can really talk about it. So the question is, well, what can we do at this point? Now, if we know the analytical expression for our function, as in if we've just solved it and we know it's an exponential, it's exponential 3.5 times x incidentally, then we can identify the values of x of interest. However, we could ignore the measurement error and we could just invert it. That's the inversion process. I found this value of x here, that little green bit, gives me a value of my function, f, which matches my observed data. However, this would be bad. This is incorrect. This particular measurement, there's nothing special about it. It's been measured with error. If I were to measure it again, I'd get a slightly higher result or a slightly lower result. So to just invert it exactly without error would be very misleading. This value of x would not sort of hold up under scrutiny. For example, if my model had a second output, or I wanted to predict with it, using just this value of x would give me quite rapidly wrong results or inconsistent results. Really, we want to take account of the errors. So we want to identify all the values of x that are consistent with this measurement plus or minus its errors. So we take our model and we basically just invert it and we get this nice region here. So we refer to the red region here as the implausible regions. We'll show you how to do that in a second. And the green region as the non-implausible. That means we haven't ruled them out just yet. We'll give reason to that notation there very soon. But anyway, there's another form of uncertainty. That's just about observational error. The other thing you can consider is your model actually correct? Because your model might be very simple and you're a bit worried about it being quite incorrect. So our framework allows you to incorporate the fact that your model isn't quite right as well, which you may feel is important. You may not, but that would widen your little green interval here a little bit if you want to do that. So we'll mention that a bit more in a second, but we're not going to dwell on that too much. So that all seems fine, but of course, that is not the game we are in when we do epidemiological models, because for more realistic models, we do not know the full analytic solution for f of x. That picture is trivially easy. Instead, for fixed values of x, we would solve f of x numerically, as in you'd run your model, and this can be too slow even for relatively fast models. So what do I mean by that? Well, if x was high dimensional, and just there I was talking about a one-dimensional x, my first set of pictures had a two-dimensional x, but the model we're going to look at, there's going to be 22 input parameters. Well, then we'd need a vast number of evaluations of the model to fill this 22-dimensional space. Just to get your head around it, if I did a 10 by 10 by 10 grids, that'd be 10 to the 22 model evaluations, which is just huge. You know, we couldn't do it. All of humanity couldn't really run that using all the computers on the planet. We'd need over 4 million model evaluations just to hit the corners. If you have 22 dimensions and you just want to hit the corners of that box, well, there's 4 corners in 2D, there's like 8 in 3D, there's 2 to the power 22 in 22D, which equates to over 4 million. So even just finding the corners is a nightmare. So what do? Well, this is where we bring in an emulator. An emulator is a statistical construct that mimics the model, but which is extremely fast to evaluate. So we bring in a statistical function that mimics our function f of x, but it's dead quick. And it's quick in ways that are nice. We can use the emulator to learn about x, as we now describe. So this is a major core piece of this whole framework. It's getting around the speed and dimension problem using emulators. So consider our graph of f of x. It's that same graph we had there before, if you remember the colored 5 points, but we don't have the analytic solution, so we don't know what's going on in between these points. Instead, we only have a finite number of runs of the model, in this case 5, 1, 2, 3, 4, 5. So this is you evaluating your disease model, and it might take seconds, it might take minutes, it might take hours, depending on the model. Now, here's the thing. An emulator can be used to represent our beliefs about the behavior of the model at untested values of x, and it's fast to evaluate. So that's what we're like with our runs. This is what we're like with an emulator. An emulator says, if you tell me you think the function is a bit smooth, I will interpolate in between these points using this blue line. And the emulator gives you the expected value of f of x. That is the blue line. And this is it's a Bayesian statement about where we expect the function to be. But along with a credible interval for f, which is the red line tells us, well, the emulator gives a statement of uncertainty about how sure or uncertain it is. And if our model is a deterministic model like this one, then when we get close to a pink dot, the emulator gets very, very sure because it says, well, we've done a run here and I know what the hell's going on here. But when we go further away between two dots, like here, the emulator gets more uncertain. Okay, so this is what an emulator does. Now, I've inflated the uncertainties for this sort of graph. An emulator would very easily pick up an exponential, but I've inflated these uncertainties so you can kind of see what's going on here. Now, comparing the emulator to the observed measurement, there's that observed measurement. I've decreased the errors a little bit just for clarity. We again identify the set of X values currently consistent with this data. So we use the emulator to tell us about good values of X. I don't need to evaluate my model. Remember, that could take me too long. I evaluate my emulator, which means evaluating this blue line and this red line, which I can do. I can do hundreds of these a second. They're really, really fast. So I evaluate the emulator on lots of X values, and it tells me where things might be good, and it tells me where things are definitely bad. Now, the uncertainty on X now partially includes the uncertainty on the emulator. When the emulator is not sure, like it thinks it's a bit high here, but the red line says, well, it could be. So the emulator says, okay, we're going to classify that as could be good. So our statement now includes the fact that we're using an emulator and its uncertainty. Fantastic. So what do we then do? Do we stop? Well, some of us do stop at that. They set up an emulator, run the analysis, and say, here's your input space, and this is what we think. But we think that's a bit crazy because the good thing about emulators is they tell you how to help them learn. By the way, these are sort of GP style emulators. The machine learning community love this stuff. They've taken this sort of emulator idea and really, really run with it. And because they're brilliant for learning, they're brilliant for representing, you can do lots of cool stuff. So here's a process of it learning. We want to train the emulator a bit more. So we do further runs within the green region, just in the green region, and they will teach our emulator much more about the function just in the region of interest. We don't need to learn over here. We know this area is rubbish and this area is rubbish. We just want to learn here. And now we have an emulator which is highly accurate, more accurate than our observed errors. So now our green region is pretty much close to the sort of truth, if you will. The emulator uncertainty is tiny. Now, note a very important thing here. When we try to learn about emulators, we don't always just put runs where we think the best guess is going to be. No, we put runs where we think it'll be most informative to leave us with a good emulator. So doing runs when you're using emulator is not like picking good runs. It's not like that. You do spread out runs designed to inform a very good emulator, designed to allow you to find these answers for your parameters to your model. Brilliant. Okay, now for a real model, one quick aside. That was a nice example so we could see the exponential shape, but that's a very boring shape. Emulators, of course, can handle all sorts of shapes. Now in 1D, there's a sine wave, there's an emulator, similar process, there's some measurements. That incidentally is the implausibility measure we actually use. Oh, sorry, if I can get rid of that. Oops, that's always the way, my apologies. That's actually the implausibility measure we use, but basically you get this green and red region and that's all cool. And if we just do the same sort of setup, here we go. I learn a bit more about my emulator. My emulator nails this whole part of the sine function, and I get these nice green regions there. I'm sorry, I've got a little bit hidden behind there. But basically, you can see it can handle lots of different types of shapes. Now, the good thing is emulators don't just do 1D functions. That would be really rubbish. They're good for higher dimensional functions too. Okay, so that is the sort of warm-up part of the talk, which basically shows you what's going on in one dimension. And now we're just going to apply it to some actual disease models. So we're going to history match an HIV disease model known as Mequano. So we're going to take those ideas and we're going to apply it to this model. So we're going to learn about acceptable inputs X to this model using observed data Z. So Z is just that observed data, the little data point that we have. We're just going to call it Z. You'll see that in a couple of formulas soon. We're going to use emulators and implausibility measures to cut our input space iteratively. And we will discuss relevant uncertainties, model discrepancy, observed errors, function uncertainty, et cetera, which feed into this. Now, it's totally described in this paper here if you're interested. There's more papers to come soon. So now this is our sort of first approach when we went into epidemiology with Richard White and Nicky McCreesh. And we did this, and it sort of, I'll show you how it went. And then we sort of refined things and built HMER. So that will come sort of towards the end of the talk. Fantastic. So I've got a couple of slides with some more details, which obviously you'll have these slides afterwards. And these slides, I'm not going to talk through much, but they've just got sort of more details about why things are cool. So this slide just tells you a little bit about the space that we're trying to identify. We call this good space, that sort of green space. We call it sort of chi. That's the set of all our good inputs. Often it can be tiny, but often it can be empty, right? Often the model doesn't exist. We don't presuppose any such input exists. Now that differentiates this technique from more standard sort of Bayesian techniques, such as full Bayesian calibration. That would be when you find a posterior distribution of your input space of interest. Many of you may have done that or done techniques like that. That technique assumes that there is some decent input and gives you a probability over it. So there's more issues about that, but I'm not going to dwell on them. All I direct you to is these two papers. This is a comparison of history matching with ABC, if you've ever used ABC. And this paper talks a lot about history matching versus sort of Bayesian MCMC and the Bayesian paradigm. Now, we're very happy to talk about these comparisons, but I don't think we quite have time today. Fantastic. So Mequano model descriptions. This is a dynamic stochastic HIV type model. It's got 22 input parameters, contact rates, concurrency parameters, relationship duration, et cetera, et cetera, et cetera. Again, I'm not an epidemiologist. Richard's and Nikki are experts in this. For me, I see that it's got 22 input parameters and it's got 18 outputs, including population size, HIV prevalence, prevalence of men and women, and long, short duration partnerships. It's a very rich, very interesting model. But the runtime is anywhere from 10 minutes to 3 hours for one simulator run. So that's actually, that could take a while, right? There's no way we can cover 22-dimensional input space if we're taking 3 hours for run. We can't even cover that space if it takes 1 second to run, incidentally. That's even too slow. So we're going to need to use emulators to get around this. Calibration data provided by general population cohort in Uganda. So that's a set of the input parameters. There's 22 of them. That's a set of the outputs. There's 18 of them with target ranges based on data with uncertainties. So that's our game. Find values for these 22 guys here to hit these 18 targets here and see how we get on. So I'm just going to link this to that 1D example so you can see where I am. In the 1D example, we set up like 5 runs with a little target data set. Well, let's look at the same thing for the Mequano model. Here's time on the x-axis. Here's 3 target data sets, 3 target bits of data. This is male HIV prevalence. And we do 1 run on the model, it looks like this. We do another run, a third run, it looks like this. We do a lot of runs, and it looks like this. And none of them are particularly close to the data. So that's us kind of evaluating a lot of runs, and nothing looks great at the moment. How we actually evaluated those, how you choose them in 22 dimensions is a whole world in itself, is a whole game in itself. And we use what's called Latin hypercubes. So maximum and Latin hypercube designs, they're a nice generic design. We have many other types incidentally too, but this is the sort of vanilla version. These spread out runs nicely over your parameter space. That's your parameter 1, parameter 2. They spread things out in very nice ways. They're good for emulator construction, and they're sort of quite, they've got quite nice properties. Various mysterious ways, which we can talk about if you're interested. But even then, they spread things out, and there's just lots of runs which are way too high, and still things don't look great. But anyway, let's think about what we did next with our simple model. We had that, and then we said, well, okay, our situation was we care about where the model is close to the data, so this bit here, and then we said, let's view this graph here as a function of x. And if you remember, we then said, well, what about these observed errors? We've got observed errors, and we might even have well, that's the inverse problem where we said we shouldn't ignore the errors. And then we said, okay, that's really what we want to do. We might have some uncertainties on the model as well. So we had uncertainties on the data, uncertainties on the model. So I'm just going to flash up a slide to show you where that sort of comes in the mathematics. Again, I don't want to sort of spend too long on the maths today, but that's all in our papers. So if you remember, we took that function and said, we're going to represent the function that we care about at each of those time points of interest as a function of x, where now x is 22 dimensional. So we represent the model as a function which maps the vector of 22 inputs x to the vector of 18 outputs f of x. So x has got a whole list of 22 things in it, f has got a list of 18 things in it. We use the best input approach to link the model to the real system y. The real system y is actually what is going on in Uganda at the time, via the following. We basically say that we think the real Uganda looks like our model evaluated at some good inputs plus some extra model discrepancy, we call it. This term epsilon is to acknowledge the fact that the model isn't quite true, okay? And you can think about that a bit more. You can turn it off in HMER if you don't like it, but you can have it in, because basically, normally the models aren't quite right. So we want to build that into our inference because it makes our inference more accurate and more robust. Second thing is a bit more familiar. We say we're going to measure the true system, so the sort of true underlying prevalence in Uganda on a particular time. We're going to measure it to get observational data Z. So there's the true system, but our measurements are not the same as the true system. They're observed with error. So one can use various different models for this, but a very simple one is additive error, where E is a random variable, which says there's the real system. It's been perturbed by some random variable, which has got some mean and some variance or whatever, which kicks things around. So Z isn't quite right. That generates your observational error, or that generates the errors on the pink lines. So that is generated by little e, that's generated by epsilon. So that's just where it creeps in. But I don't want to, there's some details about this, about how one can assess this in a paper which teaches you how to assess these if you're interested. But again, I don't want to dwell on this too much today because we've got much to get through. So consider the graph of f of x. We then looked at this point here, and remember the key point, we then said we need to cover this space with an emulator. That was the key sort of structure which helps us. So here's just a couple more details about emulators. For each of the 18 outputs of interest, we pick active variables xa, so they would be a subset of our 22 inputs, which we think are most important for each of the outputs in question. So for output 1, we'd maybe pick the first 5 inputs or the first 10 or something. And for output 2, we'd pick a different set. And then we emulate univariately at first for each output fi of x using the following. So I've labeled each output. This little I goes from 1 to 18. It kind of like labels which one we're talking about. And we use this structure here. Now, if you're not familiar with these things, that will look a bit weird. But all I'd say is the first bit is some sort of regression global term. Quite often we use, or for McWanner, we use third order polynomials. But you can use any sort of basis function you think is right. That's like doing regression on the behavior of the model. U of xa is a weakly stationary process. That's similar to a Gaussian process if you work with those things. But weakly stationary, as in we only require on its second order structure to be decent. As in it has an expectation and a covariant structure. That's which does the sort of magic of making emulators really fit data of a wide variety of forms. And the last bit is a nugget, which models the effect of having inactive variables as random noise if you're in a deterministic model. This guy would also model some of the stochasticity if you're in a stochastic model. So 3 pieces: global, local, kind of noisy, stochastic. And these 3 pieces interplay and make a very powerful emulator. Now that's the sort of structure of the emulator. The stationary process bit has this covariant structure, which you can choose different forms for. That basically says, do you think the function's smooth? Do you think it's kind of wiggly? Do you think it's really smooth? Do you think it's stochastic? You change this accordingly. And HMER just kind of does this for you, or you can pick ones if you want. But here's the bottom line is, the emulators give the expectation f of x. So that's our blue line on those plots. That's our kind of guess for f of x. And our variance var of f of x at point x for each output given by I is 1 to 18, and they're dead fast to evaluate. So that object there is that blue line which we saw there. That's the blue line there. And the width of this interval is related to the variance here. Now, there's a couple more technicalities about this. So how do we set the emulator up? Well, we train it on a set of runs. We do n runs. In that example, we did 5 runs, and we trained the emulator on that. 5 runs, we stack them in this vector called d. So look, those are the locations of the runs, x1 to xn. Those are the outputs of the runs, fi of each of them. So that's our information. And then we can train our emulator. Now, if we're full Bayesians, we can train our emulator using Bayes' theorem. I'm not going to dwell on these details, but that's Bayes' theorem there. You can use Gaussian processes, which is the full Bayesian equivalent, and that's all fine. However, often that involves a lot of complex specifications of the joint prior distributions over all of these things which are in your analysis. And that can be quite complicated and quite hard to justify robustness. So there is a better way. If we're interested to just specify the expectations, variances, and covariances of the parts of the emulator, then we can use Bayes' linear methodology. And this is what we use in HMER. And this is an alternative version of Bayesian statistics that is easier to specify and far easier to calculate with. It all just uses linear algebra, which is helpful. So we use these 2 update equations instead of Bayes' theorem. They're related, incidentally. And this is how we get our emulator expectation and our emulator variance. And they just come from these equations, and each of these pieces are built up from those previous emulator equations on the previous slides. So that's the bottom line. There's a paper which tells you more details, but you just want to realize that those are the equations which give you this, which we're going to use in a second. So that's how we build our emulator. It's built from those equations, and that's all fine. Now, a quick aside on stochastic models. Today is mainly about deterministic models. That's what most of the thing is about. Andy's going to talk a little bit about stochastics at the end of the day. So a quick one on that. These slides are sort of details, but there's different ways to do stochastics. There's different papers here which sort of tell you different approaches. But essentially summarized by this picture. Here's 13 runs of the model with lots of repetitions of each run. And you can see for a stochastic model, you have this additional thing that the function has spread at each input point. So one can just emulate the means of each of these points and give some just standard spread to each of them, but that's a bit rubbish. Instead, a more sophisticated way is to emulate their means and emulate their spreads, their variances, so you can understand exactly where they are lying and also how dispersed they are. So that's the sort of capability of HMER right now, but there's a lot more to do on this front, but that's just a little taster. Fantastic. Okay, so we set up our emulator. We have our observations. If you notice, we then painted the axis with the green and red color here. How did we paint this axis? Well, we use what's called an implausibility measure. So this is the last kind of technical thing I want to show you. Then we'll just show you some plots for the couple of examples. So an implausibility measure looks like this. It takes the emulator expectation, that was our blue line, and looks at the distance between that and the observed data, and just says, if that is high, then we have a problem. This value of X will be bad, and we paint it red. So that is literally saying, if that's the emulator expectation, that's the observed data. This is a big distance. And then this is rubbish X value and paint it red. But it standardized it by all those uncertainties. There's the emulator uncertainty. There's the model discrepancy. There's the observed error. So the bottom line is that large values of I of X imply that we are highly unlikely to obtain acceptable matches between model output and observed data input X. Small values of X do not imply that X is good. They just say that we can't rule them out just yet. As we learn more about the emulator, we may rule them out later. Hence, we refer to large values as implausible, small values as non-implausible, a deliberate double negative, and to get this point. Or if you have a stochastic model, you get an extra variance there due to the stochasticity. If you've emulated that stochasticity as a function of X, it looks like that. But we won't talk about that too much. We can combine implausibility measures in various ways. We can just maximize over them, and that's all fine. And then we just threshold on them using a very cunning rule called Puckelsheim's 3 sigma rule. Again, I'm rushing through these details, but it's all in the paper. I just want you to see that it's kind of there. That tells us decent cutoffs we can use to say how large the implausibility would be before we think it's a problem. And there's more sophisticated things we can do. We can do multivariate measures, which look like Mahalanobis distances, which can pick up joint correlations and all sorts of sophisticated stuff, but that's not really what we want to talk about today. So that basically includes all our ingredients in that picture. That gives us the sort of features of it. So now we just did that for Mokwano, combine the implausibility measures, and now we can do things like, well, the basic thing would just be to blitzing the input space with the emulator, painting all the points that are bad red with high implausibility, painting the lower ones yellow or green to get a rough idea of where things are good. This picture is a bit sort of hazy. It's a bit sort of, well, a bit rubbish. We can do a bit better than this, but it gives you a broad idea of where the action is at. Oh, that's one of the inputs, by the way. And that's another one of the inputs. And this is just colored by implausibility. So we can look at the sort of depth of the region where the space is if we want to, and we can look at sort of, so where all the sort of good fitting runs are if we want to. We can turn our emulators, incidentally, at this point, we can run them through MCMC and do a Bayesian posterior at this point if we want to. That's absolutely fine because our emulator is fast enough to do that. So that's sort of available to us. But anyway, we did that for Mokwano, and we learned about the input space. But remember, we had this key point where we had our 1D model and we did further runs. We actually annoyingly coined the term a second iteration or wave of runs. So we do a second wave and a third wave of runs. Sadly, that terminology, we coined it in 2010 for galaxy formation stuff. That terminology has now clashed very much with COVID and the waves in COVID. But anyway, further iterations of runs. So here's our Mokwano model after one wave of runs. So that's one set of runs and one emulator. And then we do a second wave. Sorry, this is now wave 4. And then this is now wave 7. So you get this progression, wave 1, wave 4, wave 7. And you see we start learning more and more and more about the input space. Those are all the inputs, by the way. All these little panels are 2-dimensional projections of the input space. Now, that's wave 9. I think that's where we got to. So you see the principle. We learn more and more and more. We do more runs, but we do more runs just where the action is at. We don't waste runs in parts of the space that we know to be bad. Okay. Now, the iterative history matching for reducing input space algorithm is here. You can have a look at it. Essentially, it says you keep doing more points until your emulators are accurate enough, or you rule the model out. That's all fine. There are reasons why this works here, which sadly I won't have that too much time to go through. But essentially, as we zoom in, we expect the model to be easier to emulate, and we have a higher density of runs in that zoomed in region. So our stationary process in the emulator gets better. The model gets smoother, so that's the sort of regression global term gets better. And we get better at identifying active variables, and we can hence emulate outputs that we might not have been able to emulate previously. The way we set up our approach, we don't need to emulate everything in one go. We could emulate, like, say, 5 outputs to start with that are easy, cut out lots of space on those, and then we can try to emulate tougher outputs that were unable to be emulated initially. We can emulate those in later waves. You might imagine there's an output that does really weird things in certain corners. It's very hard to emulate it. But once we cut out those corners due to other easy outputs, then it becomes very easy to emulate. So this is a divide and conquer approach, which is really important for high dimensional models, because otherwise you have to do everything all at once. And that can just take you like a billion runs in wave 1. Otherwise you have nothing. So that can be a real game. Okay, but anyway, let's get down to some results. You've been very patient with me. We've got about 6 minutes till the end of my talk. So I'm just going to show you results on this and then show you results on a TB model where we refined what we did and we used HMER, and that was all kind of cool. So that was our first wave of runs for Mukwano. There's some targets. And we did a few more waves, and you see we get the yellow runs, the blue runs, and the green runs. And this is what we're starting to get by wave 8. We did one more wave 9 just to nail them. But you see, to start with, none of the runs were even close. Once you do this refined process, then you get lots of runs in your sort of region that you care about. Now, there was then Mukwano 2.0. I just want to throw this in. I'm going to flash through it because this was a larger version of Mukwano, which had 96 inputs and 50 outputs. So I would describe 96 inputs as a fairly healthy number. Large parameter space means different things these days, depending on who you talk to. But 96 inputs for a disease model is decent. So we went through this, and that was all fine. Again, we got lots of nice runs, fitting the data. There's some specific plots showing how we're fitting the input parameters. Really, I just want to show you this. With this stuff, you get a very rich set of plots showing you the details of your input space. So here's input 66, input 70, input 75, and you can zoom in on which inputs are really constrained, which ones have been you've really learned about, and then show which inputs you've learned very little about. Input 58, we've hardly learned at all. Input 55, we've learned a ton about. It's incredibly squashed. And you can look at the sort of correlations between these and see what's going on. So there's a rich set of information we get out of this. So that's what we did. And that's sort of zoomed in pictures of a couple of those. So you can see the shape of the input space and how the constraints are. Now that's what we did in our first sort of few sort of projects on this. And that's all great. But then thankfully, thanks to Nikki, again, we got further funding, welcome funding for 3 more years to automate the above process, because the above process is all fun. But really, to roll it out, we want you guys to be able to use it without much input from a statistician. Although do talk to statisticians if you can. Don't make us like redundant, that would be a shame. So we then developed the HMER package with welcome funding to automate the above emulation and history matching methods. So we applied it to several test cases. Then we applied it to a large TB transmission model, which is compartmental, dynamic, deterministic, but which had 115 countries to match to. So this was a model of sort of medium complexity, although deterministic, which makes it easier. But it had 115 scenarios that we want to match to. So that's 115 separate calibration problems. So in which case, this becomes important. And this was used to inform WHO on effective TB vaccination strategies. Papers are out. We'll cite them here. And this represents 115 separate calibration problems. So automation is very important. So we ran HMER on this, and it found lots and lots of matches in 105 of the countries, and showed the conflicts that prevented matches in the remaining countries. So there are other countries where we suspected the model does not match the data, and HMER can kind of show you where the conflicts are arising. So that's out in this preprint. Have a look at it there. And there's another paper which shows the actual epidemiological results if you're interested. That's the structure of the model here. Again, lots of compartments, lots of inputs, lots of parameters. Again, I forget how many parameters are in this model, but quite a few. But let's just cut to the chase. So here we have 9 targets of the model for one of those 115 countries. So those are our 9 targets. They're sort of TB notifications at different age groups for certain times, et cetera, et cetera, et cetera. And those targets are given by these white error bars here and here and here. When we do our initial wave of runs, wave 0, and those are the dark red runs here. So they're runs which are up here and they're down here and they're spread all over the place. And if you notice, this is on a log scale. So these dark red runs are miles away. I mean, they're way above the data, way below the data, because we've blitzed the input space with sort of runs, not blitzed it, but done a design of runs. We've got runs high and low. But then we do wave 1, 2, 3, 4, 5, 6, 7. And of course, the emulators tell us to zoom in to these runs, and then they get close, and then they get really close. And then we get down to about a wave 7, and we get lots of runs that just nail these white targets, because the emulators learnt about where in input space we need to be to hit these things. It's at this point we can just look at that input space, that's fine. We could use our emulators, as I say, run it through MCMC if you want to do Bayesian posteriors, but we warn you that requires more assumptions, which you may find hard to justify, but you could if you want to. Anyway, bottom line is, what does HMER do for you? It produces plots like that automatically. It produces plots like this. So this is a plot of the input space. Here are some of the inputs of the model, kind of interesting ones. Here are the waves going from 0 up to 7. So to start with, this is now our input space. So this is a 2D projection with this guy on the x-axis and this guy, what is that, natural cure rate on the y-axis, treatment rate on the x-axis. We start off with our dark red runs, which are all over the space. We emulate, we do more runs, we emulate, we do more runs, we emulate, we do more, and we get down to this nice region here, which has lots and lots of runs which match the data. And this is where your parameters need to be to match the data. This is where your posterior would lie. This is the sort of the non-implausible region at the end of the analysis. And HMER just does this plot for you. So I've just got a couple more plots than a conclusion slides. HMER does a lot of other things because there's a lot of other analysis one can do. So for example, that's the 1D marginal on each of these parameters. So that parameter there, it's really got to be where that black histogram is there. So it's really got to be around about this interval here. And you can see the progression of the history match as we go through wave after wave. And that's us sort of getting towards the target point at the end. The other thing that we can look at, there's many other things we can look at, but one of which is we can look at the behavior of the model in output space as we go through these waves. So this is a similar sort of plot, but now what we've got on all these axes is the outputs of the model, not the inputs, so the target outputs. So let's pick one. Let's pick like this guy here. We've got TB incidence for the ages between 0 to 14. That is now on the x-axis of this panel. And on the y-axis is this guy, the proportion of TB subclinical on the y-axis. So this is now two outputs. It's a two-dimensional projection of the outputs. So they had targets, if you remember. They each had targets, target intervals. Well, in a 2D plot, those target intervals become a little square. Incidentally, a square if we're doing things univariately. Some of our other implausibility measures, this would be like an ellipsoid, if you will. But at the moment, they're squares. So we can watch how the runs progress through our waves. We have runs which are kind of like everywhere, and then they zoom in a bit, zoom in a bit, zoom in a bit, and then get into our target region. So we can see various structures with this. For example, we can see plots like this one here, where we see these two outputs are heavily correlated. And below the diagonal, by the way, is the full space. Above the diagonal is the space sort of normalized, so the red square is a reasonable size. So you can see these two outputs are heavily correlated, which is fine because the red square overlaps them, and that's all good. So we find lots of points in there, and everyone's a winner. However, you could imagine there could be a situation where this red square is off this diagonal, in which case you can see instantly that there's a problem. So for 105 countries, we found pictures like this. We got lots of runs which fitted, everyone's a winner. But for 10 of the countries, one, we found the data was just weird and corrupt. For 9 of the countries, we're able to show situations where we thought the model did not fit. For example, take these situations here. That's an output plot, just like what we're seeing. There's bunches of runs, 1, 2, 3, 4, 5, 6 waves. These are all the runs. This is TB notification for young people, TB notification for elder people. And the target data is over here. And it is miles away from what the model can do. So it would seem like, for example, there may be, I don't know, an undercount on the notifications for this age group. And the model is saying it should be up here. Maybe there's a dramatic undercount, and that's what's causing this discrepancy. But you can look at your model and you can see, aha, I think I know why my model's broken or it's not doing the job, et cetera, et cetera, et cetera. Other times you get cases like this one here, much more close, where you're thinking, well, maybe points might just creep in, but we're getting very, very close, and we've done a lot of waves, and it seems like there is a wall in the model output space. Again, these outputs are being constrained by all the other outputs we are simultaneously fitting. But you start to see that there's a wall there, and you can see how close you're getting. Maybe you look at your observed errors and say, maybe our observed errors need to be a little bit bigger. So there's a lot of interpretation you can do. Right, that's basically it. So just to summarize, I'm sorry, I'm a couple of minutes over. We have a broad, it's embarrassing to say, but we won some awards for this stuff. But anyway, a broad award-winning, with quotation marks, methodology for performing full uncertainty analysis on such complex models of disease. The emulation and history matching methods we described can be used to efficiently explore input space, as well as explore model features like we've just seen, which is helpful when developing models. The correct treatment of uncertainty is vital. Without this, any analysis will be problematic and untrustworthy. If those errors aren't quite right, it undermines the meaning of your analysis. So all we'd say is do take care about your error specifications. All of this is now in the HMER package, which you will learn today. HMER can identify lots of good matches, like those 105 countries, or alert you as to when matches may not be possible. So as we just saw, which happened in those 9 countries in the attached papers. And a final point I just say is this is HMER at version 1.0.1. So this is us just bringing it to you. So there's many more improvements to come, noticeably on speed, full stochasticity treatment. It does some stochasticity, but not as much as one could do. And we haven't parallelized it yet, so there's huge advances to be made there. And there's multi-level emulation techniques which will come. So there's lots more fun stuff to come, but we'd really love your input today, just to tell us what's good and what's bad, and to help us make it even better. Lots more references here on the development of this methodology if you're interested, but I'll just leave it there for now. Thank you very much.